Hello everyone, I am Sishun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about Kalman filter, a popular algorithm for estimating some unknown variables given the measurements observed over time. Kalman filter was proposed by R.E. Kalman in 1960 and has been widely used in many applications. The outline of this video includes introduction about what is Kalman filter and its main idea, Gaussian distribution about the brief introduction to standard Gaussian and multivariate Gaussians for state modeling, and how the product of two Gaussians for information fusion. Kalman filter algorithm about problem statement, algorithm overview, and two main stages including prediction stage and update stage. Kalman filter is used to estimate states from the measurements observed over time in a dynamic system. Kalman filter has demonstrated its usefulness in various applications, such as visual object tracking, robot vehicle navigation, or data prediction tasks. The benefit of using Kalman filter is that it estimates the state in a recursive manner. This makes the Kalman filter very fast because of without reprocessing all data at each time, and light on memory because of without storing all previous data. Besides, it provides good estimates from the measurements with uncertainty. In other words, it provides optimal estimate in linear system and qualifies estimate in nonlinear system. To achieve this, the main idea of Kalman filter is to combine the estimates from two sources that are with uncertainty. One estimator is from prediction, that involves from the estimator at the previous time. The other one is from measurement, that perceives the system state by sensors. Thus, the provided estimator after fusion is with less uncertainty than both from two sources. For example, in one-dimension tracking, we want to estimate its position p and the velocity v. X is referred to as state that consists of all variables p and v to be estimated in a matrix form. For giving the estimator of the state at time t-1, we want to compute the estimator of the state at time t. The Kalman filter firstly involves st-head from st-1 head by prediction, and then measures the state as zt head. Finally, the prediction and the measurement are fused to produce st head. The way to estimate st+1 head is the same as estimation of st head. Similarly, we obtain the st+1 minus head by prediction, and then measures zt+1 head. After that, we combine the prediction and the measurement into st+1 head, that is the estimator of the state at time t+1. Under such idea, Kalman filter models an estimator with uncertainty by a Gaussian distribution. For example, each of these three estimates is described by a Gaussian distribution. The fusion of two estimates from the prediction and the measurement is via the product of two Gaussians. Before to detail the common filter algorithm, we firstly introduce the Gaussian distribution and the product of two Gaussians. A random variable S is Gaussian if its probability density function satisfies this equation, where mu is mean and the sigma square is variance. Let three samples drawn from S be 3.0, 4.0, and 2.0. The mean mu and the variance sigma square can be computed as these two equations, and are equal to 3.0 and about 0.67 respectively. Accordingly, the Gaussian distribution of X can be expressed as this equation. This figure shows the curve of this Gaussian distribution. Mu denotes the value with the most probability, and the sigma square denotes the width of the Gaussian distribution. The larger the variance is, the wider the width of the distribution is. Hence, the Kalman filter uses mu and the sigma square to model an estimate of a random variable S. Mu denotes the most likely estimate, and the sigma square denotes the estimation uncertainty. Next, we introduce multivariant Gaussian. For an n-dimensional random vector X, it is Gaussian if its probability density function satisfies this equation, where mu is mean vector and sigma is covariance matrix. Let S1, S2, and S3 be three samples of 2D random vector X. Here shows the computation of mean vector mu and the definition of the covariance matrix sigma. In this example, the computation of sigma is shown as this equation and equal to this matrix. Similar to standard Gaussian, the mean vector mu and the covariance matrix sigma of a multivariant Gaussian can be used to model an estimate S hat of a random vector X. Mu and sigma denote the most likely estimate and estimation uncertainty of S. In this example, an estimate at time t of the state S that consists of P and V can be modeled by a multivariant Gaussian. For multivariant Gaussian, we introduce two formulas that are used in Kalman filter. The first one is called the multiplication formula. If we multiply every point in a distribution by a matrix A, we have a Gaussian with the mean equal to A mu and the covariance matrix equal to A times sigma times A transpose. The other one is called the addition formula that adds a matrix V to every point, makes the mean become mu plus V, and the covariance matrix unchanged. After introducing the Gaussian distribution, we talk about the product of two Gaussians that is used for information fusion in Kalman filter. Let x and y be two Gaussian random variables. They are modeled as eta of mu s, sigma s squared, and eta of mu y, sigma y squared respectively. By multiplying x and y together, we have a product of x and y that is scaled Gaussian, with mean mu sy and the variance sigma sy squared, where mu sy and sigma sy squared can be respectively expressed as these two equations. One property of Gaussian product is that multiplying two Gaussians results in a smaller variance sigma sy squared. We show the proof of this property. Firstly, we subtract sigma s squared from sigma sy squared. By reducing to a common denominator, we obtain this term, which is less than or equal to 0. This proves that sigma sy squared is less than or equal to sigma s squared. Similarly, this equation shows the proof of that sigma sy squared is also less than or equal to sigma y squared. This denotes that the uncertainty of two Gaussians is reduced by Gaussian multiplication. For mean mu sy, we rearrange it as this equation by introducing the term mu s times sigma s squared. Cancelling this term with its denominator puts mu s ahead. Like mu sy, we introduce sigma s squared times sigma s squared, cancel its denominator, and finally have this equation. To simplify the expression, let can be this term. Therefore, mu sy and sigma sy squared can be expressed as these two equations respectively. Next, we extend the derived equations from the standard Gaussian to multivariate Gaussian. Let x and y be two random vectors and are modeled by two multivariate Gaussians respectively. By replacing four notations on the left-hand side by laws on the right-hand side, the derived equations for the mean and the variance can be extended to the mean vector and the covariance matrix of the Gaussian product. Accordingly, K for multivariate Gaussian becomes this equation, where -1 denotes matrix inverse. After introducing the Gaussian distribution and the product of two Gaussians, we detail the Kalman filter algorithm for state estimation. Kalman filter algorithm is based on two assumptions. The first assumption is that the system to be estimated is linearly dynamic in two aspects. The evolution of an estimator st hat at time t from the estimator at time t-1 is linear and follows this equation. Here, ft is the state transition matrix. Bt and Ut are the control input matrix and vector respectively. Besides, the operation on st hat to produce sensor reading zt hat is also linear, as this equation, where ht is referred to as measurement matrix. These four variables, ft, bt, ut, and ht introduced here are the knowing system parameters. The second assumption made in Kalman filter is that the system is with uncertainty in two aspects. The control input to the system is noisy, and thus the noise of the control input is modeled by a random vector Wt. In addition, the sensing process is also noisy, and its noise is modeled by a random vector Vt. In Kalman filter, these two noises are both modeled as zero mean Gaussians that are with covariance matrix Q and R respectively. Q and R are the tuning parameters in Kalman filter algorithm. In one-dimension tracking example, assume that at time t, the car speeds up with acceleration at by driver. According to kinematic formula, the position pt and the velocity vt at time t can be expressed as these two equations respectively. By expressing these two equations in matrix form, we can obtain this equation. As the equation for linear prediction process, these three terms are ft, bt, and ut respectively. However, the control input may be interfered by some factors, for example, cascading. To model this, Wt is introduced in Kalman filter. That is a zero mean Gaussian with covariance matrix Q. In this case, if the radial positioning system can directly measure the position pt and the velocity vt, the measurement matrix ht is identity. Since the measurement process is assumed to be noisy, Vt is introduced to model this noise. As mentioned, Vt is a zero mean Gaussian with covariance matrix R. Based on these two assumptions, the objective of Kalman filter is to obtain the estimate st head by fusing st minus head and zt head via Gaussian multiplication. St minus head is a Gaussian involved from s sub t minus 1 head. Zt head is the measurement from major process and modeled as a Gaussian. Here gives the formal statement of Kalman filter algorithm. Given the initial estimate S0 head modeled as a Gaussian, two tuning parameters Q and R, and a sequence of measurements Z1, Z2, until Zt, the output of Kalman filter is St head, an estimate of the state S at time t. The computation of St head in Kalman filter is via two stages, prediction and update. The prediction stage predicts St minus head from the estimate at previous time t minus 1 via linear prediction process. The update stage fills St minus head and Zt head from linear major process by Gaussian multiplication. for an estimate x sub t minus 1 hat modeled by a Gaussian distribution. Prediction stage uses linear prediction equation to predict st minus hat. According to multiplication formula mentioned before, multiplying s sub t minus 1 hat by ft makes its mean vector and the covariance matrix becomes these two terms respectively. Next, according to addition formula, the term bt times ut for control input is added to the mean vector. Since the control input noise will increase the uncertainty of the prediction, Q is loss added to the covariance matrix. In short, the mean vector and the covariance matrix after prediction can be expressed as these two equations, respectively. During update stage, we firstly transform the predicted estimate st minus hat to the sensor reading z space by multiplying ht. Again, by using multiplication formula, the mean vector and the covariance matrix of xt minus hat become these two terms respectively. The next step is to model the measurement as a Gaussian distribution. Since zt hat is the measurement result and is the most likely estimate, we take it as the mean vector. As mentioned, the major process is disturbed by Gaussian noise. RT covariance matrix of noise is thus considered as the measuring uncertainty. In other words, a Gaussian for modeling measurement is with mean vector zt hat and the covariance matrix RT. The step to refine the estimate is by multiplying two Gaussians, respectively from prediction and measurement. By substituting these four terms for μs, sigma s, mu y, and sigma y in the equations for Gaussian multiplication derived before, the mean vector and the covariance matrix after multiplication can be expressed as these two equations. In addition, the term k is expressed as this equation. The Gaussian after fusion is equal to the estimate st hat mapped in the z space. That is ht times st hat. Accordingly, we replace mu fused and sigma fused by these two terms, and results in these two equations. The term mu st and sigma st are the mean vector and covariance matrix of the estimate st hat and are to be determined. To derive the mu st, we multiply ht inverse at both sides. Since this term is identity matrix, we obtain the equation for mu st. For sigma st, we firstly multiply ht inverse at both sides. Next, we multiply ht transpose inverse at the end of this term, and thus result in this equation. By applying distributive law of multiplication, we have the equation for sigma st. To simplify this expression, let kappa be ht inverse times k. Finally, we have the equations for computing the mean vector mu st and the covariance matrix sigma st. In addition, this equation is for computing kappa. Since this term is identity matrix, kappa becomes this equation. In the literature, kappa is called the common gain. Here we give a figure to illustrate the Kalman filter algorithm starting from beginning. Given the initial estimate S0 hat, we firstly evolved S1 minus hat from S0 hat by prediction, according to these two equations. Next, we obtain the measurement Z1 hat. Finally, we fuse these two estimates according to these equations and result in the estimate S1 hat. At time 2, we do the same thing to compute the estimate S2 hat. Firstly, we predict S2 minus hat by prediction stage. Then, obtain the measurement Z2 hat. And finally, fuse the S2 minus hat and Z2 hat by update stage. In this video, we introduce a well-known algorithm called the Kalman filter. This algorithm is used to estimate the state of a dynamic system in a recursive manner. Kalman filter models the estimate of the state by a Gaussian distribution and achieves the estimation by fusing two information from prediction and measurement via Gaussian multiplication. Thanks for your listening and have a nice day.